The last video in our motion unit is on the conservation of momentum. The law of conservation of momentum is really quite simple. What it tells us is that the total momentum in a system is conserved when no outside forces act on that system. And what we mean by no outside forces is that the only forces that act on the system are only within the system. Now, what does it mean for the momentum to be conserved? Well, the easiest way to say that is that the momentum before an event is equal to the momentum after an event. What do we mean by an event? That seems like a strange word. Well, most of the times when we're talking about the conservation of momentum, we're talking about collisions, when things run into each other. And that's exactly how we'll look at it in this class. Maybe the best way to describe the law of conservation of momentum is to write an equation. And it's a very simple equation. What it tells us is that the momentum before a collision, notice the notation here, P for momentum as we know, and then the subscript before showing the momentum before the event or the collision, must be equal to the momentum after the collision. That is the easiest way to show the conservation of momentum. The next two slides are simply a couple of scenarios where we're going to use the law of conservation of momentum to do a calculation. So I want you to consider this first scenario. A steel ball, mass equal to 250 grams, is rolling at 12 meters per second toward a rubber ball, mass equal to 300 grams, that is stationary. When the balls collide, the rubber ball moves at 8 meters per second in the same direction the steel ball was moving. Find the momentum and velocity of the steel ball after the collision. It is often the case that drawing a diagram in these situations will be very helpful to you. And I've done that for you here. Here is our situation before the collision. Notice we have our steel ball here that's shaded in the orange there, going to the right at 12 meters per second. And then our rubber ball, which is not shaded, is not going anywhere. And then here's our after scenario, where we have the rubber ball now going to the right at 8 meters per second. And then here's our steel ball. Notice here the question mark with meters per second. That goes back to the question. We're asked to find the momentum and the velocity of the steel ball after the collision. Now, the entire premise of any of these law of conservation of momentum calculations is this. We know that the momentum before the collision must be equal to the momentum after. And we're going to use this principle in each of these calculations that we do. So I'm just going to draw a line going down the middle here. And anything to the left of the line will represent calculations for the before situation. Anything to the right will represent calculations for after. Well, I know that the momentum before is equal to the momentum after. But in order for me to find this, I need to calculate the momenta of the two balls that are involved. So I can find the momentum of the steel ball, and again see the notation here. P for momentum and then the subscript steel to indicate the steel ball is equal to its mass times its velocity, which we're told is 250 grams times 12 meters per second. And that will give us 3,000 grams meter per second for the momentum of the steel ball. We now need to do the same thing for the rubber ball, where its momentum is also its mass times its velocity. We're told its mass is 300 grams, and then it's stationary, so it's not going anywhere. So its velocity is 0. So the initial momentum of that rubber ball is 0 gram meter per second. Now what I need to do here is find the total of those. I want to know what the total momentum before the collision is. So I need to add them together, where the total momentum is equal to the momentum of the steel ball plus the momentum of the rubber ball. So 3,000 gram meter per second plus 0 gram meter per second. That gives us 3,000 gram meter per second. So that is the total momentum of the system before the collision. Now remember our entire principle here for the conservation of momentum. We know that the momentum before the collision must be equal to the momentum after. So the fact that we know that the momentum before the collision is 3,000 grams meter per second, that tells us the total momentum after the collision. It's also 3,000 gram meter per second. And that is equal to the sum of the momentum of the steel ball and the momentum of the rubber ball. Well, considering what we know after the collision, we can find the momentum of the rubber ball because we know its mass and its velocity. So we're going to calculate that. The momentum of the rubber ball is equal to its mass times its velocity, which is 300 grams times 8 meters per second, which is 2,400 gram meter per second. Now that we know the momentum of the rubber ball, we can go back and use that to find the momentum of the steel ball. Because we know that the sum of the two must add to 3,000 grams meter per second. So that 3,000 gram meter per second is equal to the momentum of the steel ball plus the momentum of the rubber ball, which you just found as 2,400 gram meter per second. So the momentum of the steel ball has to be the difference between the two, or 600 gram meter per second. This will allow us to find the velocity of that steel ball, because we now know its momentum. So if we simply solve that equation helper for velocity, we get the velocity of the steel ball is equal to the momentum of the steel ball divided by its mass. So 600 grams meter per second divided by 250 grams. We get a velocity of 2.4 meters per second for the steel ball after the collision. So just some reminders here. The entire principle of these calculations is the momentum before must be equal to the momentum after the collision. In order to use that, we have to calculate momenta either before or after, and then apply that idea of the momentum before equals the momentum after, and then solve for whatever we're looking for. In this case, we need to find the velocity of that steel ball. So here's another problem to consider, very similar. Again, consider the following. Two dynamics cars are heading towards each other on a track. Car A, mass equal to 250 grams, is traveling to the right at 5 meters per second. Car B, mass equal to 500 grams, is traveling to the left at 4 meters per second. When they collide, the cars stick together. Determine the velocity of the cars after the collision. All right, so again, it is very helpful to sketch out a diagram of the situation, and I've done that for you. So here's our track, and here's car A shaded in orange, and we're told it's going to the right at 5 meters per second. And here's car B going to the left at 4 meters per second. Now, one thing I'll have you note here, as I have labeled the velocity of B with a negative 4 meters per second, ask yourself, why do you think that is? Why do you think I've labeled it as a negative 4 meters per second? So you've had a chance to think about this. If you said it's because it's going in the opposite direction as A, you'd be correct. By definition, because these two are traveling in the opposite direction, one of them has to have a negative velocity, where negative simply means going in the other direction as the original. It actually doesn't matter which one you call negative. You could just as easily call the first one negative, the 5 meters per second to the right as negative. But by convention, we usually say going to the right is positive. So B going to the left means it's going at a negative 4 meters per second. So that's our before scenario. After the scenario, here's what we have. We're told that the cars stick together. So here you can see A and B are stuck together. And we're asked to find the velocity of the cars after the collision. Well, based on what I'm given, I don't know which way they're going to be going, which, remember, that would also be included in velocity, because velocity is both speed and direction. So I'm asking here, notice I have an arrow drawn both directions. I want to know which way they're going, left or right. And remember, they are stuck together, so it's not as if one can go one way and the other can go the other way. They have to both go the same direction, and I also want to know how fast they're going. So once again, we need to apply that idea that the momentum before the collision must be equal to the momentum after. So to do that, we need to find the momenta of the two individual cars before the collision. So the momentum of car A is equal to its mass times its velocity, or 250 grams times 5 meters per second. That would be 1,250 grams meter per second. Likewise, I need to find the momentum of car B, which is equal to its mass times velocity, which is 300 grams, times the negative 4 meters per second. Again, remember, it's going in the opposite direction. And that will give us a negative 1,200 gram meter per second. A negative momentum is perfectly fine, because a momentum is just like a velocity, and the fact that it also includes a direction. The fact that its momentum is negative tells us that its momentum is in the opposite direction of A's. So now that we have the two momenta, we can find the total of them by adding them together. The total momentum before the collision is the momentum of A plus the momentum of B, which is 1,250 gram meter per second, plus the negative 1,200 gram meter per second for B. If you add those together, that will give you 50 gram meter per second for the total momentum of the system before the collision. Now again, recall the entire premise of all these law of conservation of momentum calculations is the total momentum before will be equal to the momentum after. So I know that the total momentum after the collision is 50 gram meters per second. That'll be the total of the two. Now again, recall that these two cars were told that they're going to stick together. So that actually makes us easier if they stick together. Here's why. We can treat the two cars as one because they're together. they have to go the same direction at the same speed because they're stuck together. So it actually decreases the number of calculations we have to do. So remember, we're asked to find their velocity after the collision. So I know that the velocity of the cars will equal their momentum, P, divided by their mass, M. Well, their momentum, we know the total is 50 gram meter per second. We determined that just a bit ago. And then dividing by their mass, because they're stuck together and I'm treating them as one, I can just use the sum of their two masses. 250 grams plus 300 grams would be 550 grams. So 50 gram meter per second divided by 550 grams, that gives you a value of 0.0909 meters per second. Now you might be asking yourself, have we found the velocity? And we have. Notice that this is positive, so that matches the positive velocity we had initially with A. So we know that the cars are going to travel to the right at 0.0909 meters per second. So we have in fact found the velocity because we're showing both speed and direction. Okay, to summarize all these calculations, the big premise in all these is that the momentum after the collision, in this case, in this last problem, 50 gram meter per second, must be equal to the momentum before, which we found as 50 gram meter per second. That's how we knew the after. Once we have that, we can find whatever value we're looking for. In this last case here, it was finding the velocity of those cars that were stuck together.